Welcome, class. Today we're going to be talking about the greenhouse effect. We're going to be able to define it as well as tell you a little bit about the four most important greenhouse gases and how they impact our atmosphere. So let's go ahead and get started. Well, let's first of all start by trying to define it, trying to tell you a little bit about what it is and how it works. I like to use the word climate change instead of global warming, but because it's a little bit broader term, because with climate change, as our current models tell us, we're going to be seeing warming in places that were cold, and we're going to be seeing places that were dry are going to be wet. So, and all of this, of course, is impacted by our cooling as well as our warming system, which is, of course, the greenhouse effect. Now, this climate change thing is been around ever since the planet has been. We always have had periods of cooling as well as warming, and they're just natural causes. Things like, for instance, every tens or hundreds of thousands of years, the Earth's orbit will change slightly because it's more elliptic. So the length of the orbit will definitely have an impact on cooling or warming. It's also a slight change in the axis, either tilted too far one way or too close in another, will also have an impact on it. And sunspots, they go through cycles of about every 11 years, where we have kind of an extra energy boost, which will sometimes warm the planet. And of course, the volcanic eruptions. When Mount St. Helens erupted in the early 80s, we had here in California 12 to 15 months of a kind of a cooling trend. So that definitely had an impact on our climate kind of locally. Now, as far as climate change is concerned, over the last few hundred to 1,000 years, we've been fairly fortunate. Our climate has been fairly stable. We didn't see much of a rise until the late 1800s, around 1880s, when the Industrial Revolution kind of got kicked off. Because we were burning more fossil fuels, in particular coal, when it was going into the atmosphere, the particulate matter was having definitely an impact. So did the CO2. But since about 1975 or so, we've seen a much more steep increase in the amount of greenhouse gases and, of course, rising temperatures as well. So we're going to be looking at that today and trying to look at some of the evidence for all of that. For instance, like, how do we know what the temperature was in the 1880s? How do we know about what the temperature was 10,000, 20,000 years ago? Because there's no written record of it. There's a couple of ways. One of the things is what scientists look at are carbon radioisotopes. Carbon, because it has a charge of 4, it can bond with itself, bond with oxygen, bond with hydrogen. It makes it an extremely interesting kind of an element. It also challenges us to use a variety of different means to see how it behaves. For instance, we have to talk about chemistry, we have to talk about biology, climatology, we have to look at oceanography, geology. We have to combine all those sciences together to really figure out what really goes on in our planet, in particular with the carbon cycle, because carbon is becoming more and more important as we look into this climate change situation that we have. But by looking at radioisotopes of carbon, we can see, for instance, what the temperature was 10 to 20,000 years ago. And in particular, if we look at rock sediments like limestone and other geological types of minerals and rocks, we can begin to decipher what was going on many thousands of years ago. Same with fossils. They have radioisotopes in them as well. And also, as plankton die, they settle to the bottom of the ocean. And we're getting to see lots of good data from ocean sediments, not only from the limestone deposits and fresh and ocean water, but also from plankton and other animals and plants that settle down there. And because there's little to no oxygen down there, many of the animals and plants that have died are in relatively good shape, and because it's so cold as well. But of recent, the one that's really been getting a lot of press is the ice cores from Antarctica. And to give you an idea of the greenhouse impact, what scientists do, they drill these cores. This is a handheld core. It's not a very deep one. They also have some mechanical ones that can go very far into to the ice pack and bring out ones that have thousands and thousands of years embedded in it. This one is one they can look at more recent times. So anyway, they just kind of crank it down like a soil auger, and as they crank it down or drill the core, what they'll have is a core full of ice. And what they have to do is that obviously they're going to have to remove it and prep it so that they can, of course, get all of the data from it. And the way they get the data from it is they slice the core into small little kind of biscuits or bits. And then what they can do is the scientists can then extract the gases that are in those bubbles, as you can see here on this picture. So what's in these little bitty holes or these little bitty bubbles is all different kinds of atmospheric gases. And when scientists look at them, they can extract that and then take a look at what the level of CO2 is, for instance, or what the parts per million at that time. They're kind of like tree rings. They're very much striated, and each in those striations, or those rings, if you will, you'll be able to count back so many years to be able to see in 1880 what was the CO2 concentration like on our planet. So that gives us, through that scientific endeavor, kind of a glimpse into the past as far as what was going on with CO2, oxygen, methane, all of those kinds of gases. Really, when we look at this whole greenhouse effect, it really is this interaction between the sun and the greenhouse gases. Those gases are the thing that's going to warm our planet, warm the troposphere, as well as the surface and the ocean. The factors that affect the greenhouse effect is, as I said before, just the sun and the oceans. As the sun beats down on the ocean, it's absorbing heat, but also is reflecting it back as well, because not all of the photons or all the infrared radiation is going to go directly into the land or the ocean. Some of it is reflected back. So as the planet will warm up based on these two factors of the sun and the ocean, it also interacts with the gases as well. To kind of give you an idea of how that works, I'm going to kind of just draw on this just a little bit. As infrared radiation goes through our atmosphere, our troposphere, some of it's going to be reflected back because it's not hitting it at the right angle. Some of it, on the other hand, is at the right angle, and it gets through clouds, and it goes through some of the water vapor and others, and it's going to start heating up the ocean. So the ocean starting to, it acts as a sink or a reservoir of heat, as well as some of the other gases. As it absorbs that, it'll radiate out some of these some of the heat. As it does, the infrared radiation sometimes will get trapped by these greenhouse gases. So it'll hit they'll hit the molecules, and they'll bounce back, and then maybe even bounce back again. Sometimes, though, gets through, radiates, let's say, the land, and then it misses some of those molecules and goes back out into space. But some of it hits some of these greenhouse gases and re-radiates, and that's the part that actually heats the planet. When it gets bounced off the greenhouse gases, and those greenhouse gases act kind of as like a sealant, and what they do is they keep it our planet nice and toasty. For instance, it's been pretty cold today, so I kept my jacket here, and I make these podcasts down in my basement. And sometimes, like days like today, it gets pretty cold. So sometimes I just wear a jacket, and this jacket all by itself does a pretty good job of keeping me warm, and I don't really need much else, or a blanket of that sort. So the greenhouse gases act like a blanket or a jacket, and if so long as there's a balance of greenhouse gases and there's some space in between them, some of the radiation can get out into space, and it keeps it fairly comfortable for us. But sometimes what happens is these gases get trapped, or what happens in some of these cases, there's an accumulation of gases, too many gases. And we'll get to that, what happens when that. But I wanted to make sure you know that there are 4 different types, or there's 4 main types of greenhouse gases. Water vapor, that's kind of the number 1. The number 2 one is carbon dioxide. And that usually is come out burning greenhouse gases, gasoline, coal, burning natural gases. Those are things that are going to be eventually be carbon dioxide. And then methane, anything that decomposes in an anaerobic condition is going to release a methane. And then of course there's nitrous oxide, and that'll come from partly from the nitrogen cycle, as waste products from animals and plants start breaking down. They give off nitrogen, and they combine with the oxygen, get nitrous oxide. So those are the 4 types. And when they in equal amounts, not necessarily equal amounts, but when they have when we don't have too much of one or the other, it's fairly comfortable on the planet. But since the 1980s, we've been putting lots and lots of carbon dioxide and methane in particular into the atmosphere. The nitrous oxide has also increased because of our use of inorganic fertilizers, because they release the nitrous oxide. Because as we fertilizing our crops, some of that just vaporizes and gets into our atmosphere. So because of deforesting or clearing our forests, fossil fuel burning, and inorganic fertilizers, we're beginning to see more and more of these greenhouse gases in our atmosphere, leaving less and less space for some of the sun's rays to bounce back into space. So what can happen is that these greenhouse gases start building up in our atmosphere. And as they build up in our atmosphere, they leave little space or little room for the radiation of the sun's rays. And when that happens, let's go back one. Go back right here. And when that happens, it's kind of like putting on extra blankets or extra kinds of, like for instance, I'm going to go ahead and put my hat on here. And as I pile on more and more insulation on my body, it's going to get warmer and warmer and warmer until it gets to a place where it really kind of gets uncomfortable. My blanket up here, 3 blankets in here. If I continue doing this, of course I get kind of overheated. And that's kind of the same thing that's going on with our planet. As the sun rays come down and bounce off of, let's say, heats up our ocean, and there's no space for it to leave, so it re-radiates. And then, of course, the sun comes down here, bounces off that, re-radiates this. So it stays, all the radiation stays in our atmosphere, in the troposphere in particular, and heats it up. So it gets warmer and warmer. So that gives you an idea of how it works. Kind of like extra blankets and an extra hat, extra coat possibly. So that gives you an idea of how that works. And let's go on. Here's a comparison between the two. As you can see here on the left-hand side, the natural greenhouse effect, there's more spaces for the re-radiated heat to get through. And when it can do that, it maintains a more constant temperature. Whereas when it's human activities or human enhanced, there's a less space for the re-radiated heat to get through, so it stays in our atmosphere and heats it up. And there is evidence that suggests that human activity is the cause of this this phenomenon of global warming. Now, the greenhouse effect always has taken place. It's a natural process, but because of our possible activity, we're warming the planet because of the extra greenhouse gases, in particular CO2. And some of the evidence that the scientists have accumulated is, for instance, the 10 most warmest years have happened since 1891. And in particular, If you take a look at this data right here, it shows us since 1990, which is right about here, we've had the top 5 most warmest temperatures or summers. Top 5 just in the last 12 years. So that should give us some cause for concern, or at least to look at it. The other thing that we've noticed as well is scientists have also been measuring since the late 50s CO2 concentrations. And the CO2 concentrations have not gone over, at least from the scientist's point of view, ever been over 300 parts per million at any particular point in time. And again, that 300 parts per million, and again, if we take a look at it, here's 300 parts per million. It hasn't started to get above that till around the 1920s. And now we're consistently in 300 parts per million. Currently, we just did this in the lab not too long ago, we get a pretty consistent 370 parts per million of CO2. Is that harmful? We've seen a little bit of a spike in the global mean temperature because of this, of course, carbon dioxide concentration. But if you take a look at this graph, it has a very close connection to the temperature graph that I just showed you. If you take a look, it has an exponential rise in CO2, about the same level that the exponential rise in the temperature also has taken place. So they're definitely related. Now, how much so? It's still kind of being researched to see if they're really indeed carbon dioxide can predict an increase in temperature because of its insulative value. And of course, all over the world, glaciers are beginning to melt. As you can see, Glacier National Park, picture taken in 1913, and then of course one 4 years ago, around the same time. The depth as well as the extent of the glacier, as you can see in these two pictures, are definitely different. And in 2008, there's very little of that glacier left. And of course, we're beginning to see more severe weather, like for instance hurricanes. We're seeing coastal areas inundated with more water because of the increase in the ocean level. So there is some evidence. Is it conclusive? They're still doing evidence, but there seems to be definitely something going on to believe that there's a change in our climate, and of course a change in the amount of CO2 in our atmosphere. Now, does that necessarily mean that someday very soon we're going to be owning beachfront property in South Dakota? Probably not. But in my next podcast, I'm going to be talking about the effects of anthropogenic global warming and what are some solutions. So I hope this has helped you understand global warming, the greenhouse gases, as well as the greenhouse effect. And we hope to see you in your lab very, very soon. And in about 2 or 3 days, I'll have the effects of global warming and, of course, what are some of the solutions. So we'll see you then. Thanks a lot.